Okay, here we go. We're starting. Here we go. Time for another lesson. Another boring lesson. Okay, guys. Can I ask you this question? Has anybody ever been in a car or been in a house where it's raining, it's a cold day, it's raining, and then the rain turns to hail? Okay, can you tell when the rain turns to hail?
Yeah.
Sure, because what does it sound like? Yeah, it sounds different. And would you say it's louder?
Yeah.
Significantly louder, right? And the first thing we're going to do is talk about why. Why is it that hail hitting the roof of your car or your house is significantly louder than rain hitting the roof of your car or house? Now, I can just haul off and do the problems and show you, but Alexis, tell me why.
More, hit harder, more force.
Beautiful. More force. That's it, pure and simple. More force. It hits with more force. So now my question is why? Why does hail hit with more force than water? Yeah. Okay, well, let me ask this. Does hail have a greater mass than the raindrops?
No.
Why not? Zena, why wouldn't hail have a greater mass than the raindrops? Okay, ice is less dense than water, but would hail have a different mass than the raindrops? Why not? What's that? What's that?
Conservation.
Yeah, conservation of mass. I mean, these raindrops are turning into the hail, right? So no, they're going to definitely have the same mass, right? So that's not it. So someone else tell me why. Why does the hail exert more force on the roof than the rain? How is hail different from rain?
It's solid.
Good, it's solid, which means when the hail hits the roof, what does it do?
Bounces off.
Good, it bounces off. When rain hits the roof, what does the rain do?
Splat.
Pretty much goes splat, right? And that's it. That's the answer. Now we're gonna end this little thing with a sort of answer that an AP exam would want to see. But that's it, pretty much. Yeah, the hail exerts more force because it bounces instead of going splat. And let's actually look at this algebraically. Okay, here, example number 1. Okay, rain hits roof of car. It's going 15 meters per second downward when it hits the roof, and then after it hits the roof, the final velocity is equal to 0, which means it goes splat. I'm going to give you the rate, the mass rate at which the rain is hitting the car. The mass rate is going to be 0.060 kilograms per second. 0.060 kilograms per second. Let me show you why I have to give you a mass rate. Here's your car. Here's the rain hitting the car. Okay? Rain hitting the car isn't like a rock hitting the car. When you drop a rock, it hits the car and that's it, you're done. The rock exerted force on the car exerted force on the rock, and then it's done. Rain is a continuous process. The rain is continually falling on the car, which means the rain is continuously exerting a force on the car, and the car is continuously exerting a force back up on the rain that's hitting the car. So we can't talk about, 6.06 kilograms of a rock hitting the car and then you're done. You got to talk about a mass rate. You're getting 60 milliliters of water hitting the car every second. And by the way, this rain is hitting the car and just going splat. So it's just going splat, 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 splat. Okay? Our task is to find the force that the rain exerts on the roof. I'm going to do this problem for you, and then you guys are going to do the hail problem. Here's what we're going to do. Force times change in time equals change in momentum. Please write that down, the impulse momentum theorem. And you know momentum is mass times the change in velocity. And this mass here would be useful if it was just a rock falling on the car. But actually it's a mass rate, it's rain continuously falling. So what would you do to both sides of this equation to make things a little bit better for myself? To make it so I can have a mass rate on the right side? What would you want me to do, Gavin? What do I do to both sides? Yes, John Carlo?
Divide by time.
Yeah, divide by time. Divide by time. So now I got force equals mass over time, or the change of time, times the final velocity minus the initial velocity. You guys see that? And now there's my mass rate, mass per unit time. And so now I can just plug in. My mass per unit time is 0.060 kilograms per second. My final velocity is 0 because it went splat, minus my initial velocity, which is negative 15 meters per second. And I get a force of 0.9 newtons. Now, this force is pointing upward because that's the force that the roof has to exert on the water. That's the force that is being exerted on the water to make it change its momentum from whatever it was to 0. So if the force is exerting 0.9 newtons up on the water, what's the water doing to the roof? According to Newton's third law of motion. If the roof's exerting 0.9 newtons up on the water, what's the water doing on the roof? Yeah, exerting 0.9 newtons down. So the water exerts 0.9 newtons down on the roof. Great. But now I'm going to give you a different problem. I'm going to give you a hail problem where the hail doesn't go splat. The final velocity is going to be 10 meters per second. And here's example 2 that I want you guys to do. Example 2, now water turns to hail. All else is the same, right? The mass rate is still equal to 0.060 kilograms per second. And the initial velocity is still negative 15 meters per second, but the final velocity is now going to be positive 10 meters per second. And I want you to find the force on the roof. So good luck. Please do it the same way. Here, I'll make a picture. This will go pretty quick. So what you guys getting? How many newtons now? How many we got? 1.5. Yay, yay. That's good enough. I mean, I know I'm going fast, but good. 1.5 newtons, significantly more force. Someone explained to me in the way a child would understand, why is my car exerting more force on the hail here? What I'm saying is don't bring in physics concepts, just bring in something that you use your common sense on. Why is my car exerting more force on the hail than on the rain? What's happening here that requires the car to exert more force? Yeah, Logan. Thank you. The hail's bouncing off the car, so the car has to push up more, right? The car has to exert more force to make that hail go up than it does just to stop the hail, just to catch the hail. Just to catch the rain. You see what I mean? So yeah, that's the way you could explain it to someone, like my daughter, more force because you got to do more with it. Okay, but there's another way I'd want you to explain it, the way an AP physics test would expect you to explain it, and they would expect you to explain it in terms of impulse momentum, And so this is the sort of thing they would want, okay? Louder sound due to more force. And that's what you guys were telling me earlier, more force. More force because with bouncing, excuse me. With bouncing, you get a bigger change in momentum. With bouncing, you get a bigger change in momentum. And force times change in time equals change in momentum. Bigger change in momentum, bigger force. That's simple. You guys okay with that? So I'm going to give you another problem where you're going to have to give me a physics 1 type explanation. Okay. You are walking on the sidewalk, minding your own business. There's a building here. There's a flower pot on the building. Flower pot. Tell me, what happens next? Absolutely. Flower pot falls on your head. Crunch. You guys okay with that? Okay, so my question to you is this. Would you prefer the flower pot to bounce off your head or break?
Either you get bloody or you get a concussion.
And please explain why. Good luck. Would you want the flower pot to bounce or break? So you've got two choices. Either the pot bounces off your head, or this flower pot will come down here and then break. So the shards all are coming down. Okay, tell me, how many people, let's have a vote. How many people say they prefer the pop to bounce off their head? How many people say they prefer to have a break? Yeah, good for you guys. And please explain why. Yes?
Because when it bounces, it requires more force to make it bounce. So,
Good.
Yeah, and braking is just braking, not bouncing.
Okay. Tell me more, yeah.
So if it were to like fall on your head and not break, your head has to exert that same amount of force to make it go off without it breaking.
Beautiful. Now, I need someone to mention impulse momentum theorem, because that's what they're going to be looking for on the crazy AP exam, yeah.
So you prefer to brake on your head because less force is needed to brake than to bounce, because there's going to be a smaller change in momentum, because your final velocity is going to equal 0 meters per second, and because force times the change in time equals the change in momentum, it'll be a smaller force.
Yeah, that'll get you full credit, baby. You're looking at a 5. Yeah, exactly. That's the sort of thing they would want. Even though what you guys are saying is correct, they would want you to say, hey, I've got a bigger change in momentum here because my velocity is changing from negative to positive. Here, in fact, what if the velocity of the shards was the same before and after it hit your head? How much force would your head have exerted on this thing if the velocity of the shards is the same before and after it hits your head? Yeah, 0. 0 force whatsoever. It's like the force you feel when a soap bubble hits your head. You know, you wouldn't feel it at all. And that's what would happen if the velocity before and after the collision with your head is the same. No force at all, right? Yeah, good. So sure, we want brake. Less force, less change in momentum, and force times change in time equals change in momentum. Just make sure you mention that. You got less force because there's less change in momentum. You could even talk about the velocities because there's less change in velocity. You know, your initial velocity and final velocities can be virtually the same if the thing hits your head and just crumples around you. Let me give you a scenario of a movie, you know, where there's a fight scene in the movie, okay? So these two guys, two cowboys, they're actors, of course, they're stuntmen. So they're in a saloon and they're fighting. And one actor picks up a bottle and hits the other actor in the head with the bottle. What does the bottle do? Break. Does it break because it's cool when bottles break? Why do you need that bottle to break? What happens to the actor if the bottle bounces off his head? If it goes conk, what's going to happen if it bounces off his head like a big thick Coke bottle? Yeah, the guy's knocked out. You need that bottle to break, right? So the other actor picks up a chair and hits the first actor in the back with the chair. What does the chair do? Yeah, it better break. You don't want that momentum of the chair to be significantly different before and after it hits the actor. And the only way that's going to happen is if the chair breaks. Right? And then the two actors fight, and they fight their way up to the top of a balcony. Then they fall off the balcony and fall on a table. What does the table do? Break. You don't want the... What if they fell on the counter? What if they fell on the... What is that called? The bar. What if they fell on the bar? Yeah, they die maybe. I mean, because they hit the bar and bounce. Could you imagine 260 pounds of Mr. Shana falling and bouncing? That would be really bad. That would take a stupendous amount of force to make me bounce in the air, and I don't want to feel that force, right? And then here's the last thing, okay? So now these actors, they're in the saloon, and the saloon has this big picture window, right? Big picture window. You know, I don't know how to make a window look like glass. You do things that make it look like glass. And so this dude, he runs through the window, and it turns out his velocity before he hit the window is the same as his velocity after he passes through the window. Tell me, how much force did the window do on him? 0. Yeah, 0. You know, as long as that window doesn't become all these knife, you know, razor sharp shards that can cut you, you'll be fine. You know, if you're going the same speed before and after, that means that window didn't exert any force on you. Yeah. Have you ever seen those fails, those vines, where someone thinks they're walking through an open, sliding door, but it turns out it's glass, and they hit it and bounce off? Well, lucky for them, because they experienced maximum force because they bounced off that window, but I don't know if they want to experience the window breaking, because then they get all cut up, and that's a big, huge bummer. Here, let me show you one more thing about braking versus bouncing, and then we're going to go on and do systems and isolated systems and conservation of momentum. When humankind discovered electricity and discovered how you could generate electricity, one way that they commonly generate electricity is with water wheels. They used to use water wheels just to mill grain. A waterfall would hit a water wheel, and through a collection of gears, the rotation of the water wheel would make some big millstone rotate, and they'd grind grain, But then they hooked up the water wheel, connected it to a loop rotating in a magnetic field, and now you have electricity. So you've got this water, and the water's going to hit here on this paddle wheel, and it's going to turn the paddle wheel, and you'll generate electricity. And notice the water's pretty much just going splat, okay? And then people decided, hey, we can do better than that. And so the best of those water wheels ended up being invented by a guy named Pelton. Whoops. Okay. So now the water's going to fall here, and tell me, what's that water going to do? It's going to collect, okay, but let's say it doesn't collect. It hits here, hits the scoop, and then where does it go? Up, correct? This water hits here and goes upward. Why is this a better water wheel than this? Say again, Noah? Yeah, more force. And why is there more force? What's that? Bouncing, yeah. Which means on an AP Physics exam, what else are you maximizing here? Change in momentum. You're going from a negative momentum to a positive momentum. That's a bigger change in momentum, from a negative momentum to zero, right? So yeah, bigger change in momentum, more force. That wheel will spin more, spin faster. You'll be able to rotate your loop in a magnetic field better, and you get more electricity. And this is the Pelton water wheel. Oops. And so I have to tell you, when about 10 years ago, my son was a little boy, my wife and I went on vacation. I think we were in Washington, the state of Washington, and we were hiking in the forest, and it was very beautiful. And then I discovered this big presentation thing about Pelton water wheels. They actually had a Pelton water wheel there in the middle of the wilderness, because there was a waterfall right there. So my wife and my son, they went on, and I said, oh honey, I've got to stay and read all about the Pelton water wheel. So that's what I did. I spent about a half hour reading about the Pelton water wheel while they went off and did their own thing, and it was beautiful. Yeah. Okay, great. Hey, any questions or comments or thoughts about bouncing? Okay, then, by the way, which famous cartoon character always bounces?
Tigger.
That's right, so Tigger knows his physics. So here we go. We're now going to talk about systems, isolated systems, and the conservation of momentum. Here we go. We learned earlier this semester, a system is the objects being studied. What you're looking at, that's your system. The way I defined it earlier this semester, I didn't say it was the objects being studied. I just said the system's whatever you want it to be. Whatever you want. Because this is America. Woo! And you can do whatever you want in America, whatever you want. And that's what a system is, whatever you want it to be. But the thing is, once you've defined what the system is, you've defined something else equally important. What else have I defined once I've defined what my system is?
Surroundings.
Yeah, the surroundings, what's not in the system. That's just as important to know as knowing what's in the system. Good. So let's say this is what I've got. I got these two guys, and these two guys are going to push against each other. Two guys pushing against each other, but not in a sexual way. They're just pushing against each other, like normal, just pushing. So let's say these two guys are my system. Or maybe it's a guy and a girl if you're more comfortable with that. It's a guy and a girl. They're going to push against each other. So now, I've got two things in the universe. I got things in my system, I got things outside my system. And so I want to talk about there's actually two types of forces, external forces and internal forces. External forces are forces that originate from outside the system. Tell me, if my system is just these two guys, what's an external force on this system? What's that?
The weight.
Sure, their weight. Because what's exerting that force, the force of their weight? What's exerting that?
Gravity.
Yeah, gravity, the Earth. And Earth isn't part of the system, right? The system is just these two guys. Can you think of another external force besides gravity? Yeah, normal force. Because the ground is exerting the normal force on them, and the ground isn't part of the system. So I want you to see, you remember how for a force you always need two things for a force, right? It takes two to tango. You need two things for a force. Two objects always required for every force. Well, if that second object is not in the system, then it's an external force. So here, let's go ahead and define that. External force originates from outside the system. That's an external force. It originates from outside the system. There's two objects responsible for a force, and one of those two objects is not in the system. Tell me, what's an example of an internal force in the system? Yeah, the push that they're exerting on each other. Absolutely. That's an internal force because one object in the system is exerting the force on another object in the system. So these are forces, they occur between objects in the system. Well, I can do force times the change in time equals the change in momentum. That's my impulse momentum theorem. But these forces, there's now two types of forces in the universe, external forces and internal forces. And so this force I'm going to rewrite as the net external force. That is what I get when I add up all my external forces, added to the net internal force. What I get when I add up all the internal forces times the change in time equals the change in momentum. And now you tell me, on any system, what's the net internal force? If I added up all the internal forces, what would I get? Why 0? Good job.
Is it because of Newton's third law?
Yeah, good for you. It's because of Newton's third law. Whatever force this guy exerts on this guy exerts the same force back on him, and those two forces are equal and opposite. They cancel. If I had a third person in this system, then whatever force he exerts on this guy exerts the same force back, and whatever force he exerts on this guy, that guy exerts the same force back. All the internal forces of a system have to cancel because of Newton's third law of motion. So it's going to be 0. The net internal force is 0 due to the third law, Newton's third law of motion. So this formula simplifies into just the net external force, which I'm going to express as the sum of the external forces times the change in time equals the change in momentum. What this is telling me right now is if I want to change the momentum of the system, I need a net external force. A net external force is required to change the momentum of a system. Internal forces will never change the momentum of a system. You need a net external force. Well, let me ask you one more question. Oh wait, no, I don't want to ask you one more question. I'm just going to go on. If the sum of the external forces equals 0, the system is isolated. If there's no net external force, the system's isolated. You tell me right now, what's the sum of the external forces? You told me two external forces, gravity and normal force. What's the sum of the external forces on this system? 0, right? Because the gravity is exactly balanced by the normal force. Net external force is 0. Now, we could make it so that the net external force isn't 0 if one of these guys decided to jump, so that now the normal force is greater than the weight on him, then the net external force would be 0. Would not be 0, the net external force would have some value. But if no one's jumping, if all they're doing is just standing there, then yeah, the net external force is 0. So this is an isolated system. Sure, there's plenty of external forces, but they all cancel, and it's an isolated system. Well, if the system's isolated, then my external force times my change in time is going to be 0, which is equal to change in momentum. That is, the momentum of an isolated system does not change. The momentum of an isolated system does not change. And so I got 0 equals the final momentum minus the initial momentum, or initial momentum equals final momentum. There's a name for that. That's called the conservation of momentum. It says simply, if a system is isolated, then momentum is conserved. That is, the initial momentum equals the final momentum. So I'll say for an isolated system, that is, the sum of the external forces is equal to 0. For an isolated system, momentum is conserved. So it's kind of reminiscent of what we learned about mechanical energy being conserved. Remember that one? In order for mechanical energy to be conserved, what had to be equal to 0? Yeah, work done by non-conservative forces. Then we get conservation of mechanical energy. Well, this is kind of analogous for an isolated system. That is, if the external force is 0, then the momentum is going to be conserved. And then what's going to happen is tomorrow, I'm going to give you 1,000,000 problems that are all conservation of momentum problems. But this was my intro. This introduced to you this idea of conservation of momentum and why it comes about, because we have systems, and specifically we have isolated systems. But like I said, none of your problems on tonight's homework are going to involve that. So, but now you know it, conservation of momentum. So what did we learn today? Well, we learned about bouncing. Tell me, what ends up becoming maximized when things are bouncing?
Force.
Yeah, force, and why is the force maximized? Because what else is maximized? Yeah, change in momentum. Good for you guys. Because the change in velocity is maximized because you're going from a negative to a positive velocity or a positive to a negative. Okay, we're done. Thanks a lot. Bye-bye. Thanks, Gavin.